for this design optimization, we have a textbook, this one. This book, I have put the PDF file on the iLearning, so you can go to iLearning to get the PDF file of this textbook. For this class, we only have homework assignments. We don't have any exam or project. So as long as you could come to the class and try to do your homework, you will get 90 grades in this class. So you will be fine. And if I assign homework, you should turn in your homework either on class, or if I assign the homework for you to take home to do, at the beginning of the class, give me your homework. So late homework will not be accepted. So unless you have very special reason. So this is the policy of this class. And in this class, you will learn how to do optimization for simple problems. Learn how to formulate, how to solve, and carry out this optimization process. And today, we will start from chapter 1. So if you have time, please read the chapter 1 of the textbook. So today is the introduction of the design process and the basic terminology and the notation we will use in the class. Design, we have, it can be, it's not very, say, there's no formula for design. But we have some concept, we have some design process. Like, we have spec first. So your boss can give you specification of the problem. Then we can do some initial study to come up some initial designs. After that, you have some, you think this design is good, then we can do detailed design to have your result, your product. Then you need to fabricate your prototype and test your prototype. Then this is to reach your final design. So pretty much in this class, we will do the detailed design. We will start here. We won't do prototype fabrication. We don't have testing part. And it's not just one-way process. It's, we have a loop. Always we will come back to, if the detailed design we find out we got problems, then we should go back to the preliminary design, initial design. Or if we have run these steps, this loop several times, still something wrong, we should go back to the spec. We may need to talk to our boss. Maybe we need to modify the specifications. Then we can get the feasible design. So this is, we say, feedback loop process. Could you read this?
Optimization concept and methods were have for at every stage of the process.
Yes. In preliminary design, we may need to do optimization. In the detailed design process, we may need to do optimization. And even you do prototype fabrications, if something goes wrong, something not quite right, you may go back to step 1, 2, 3 to revise everything. Okay. So optimization is very useful for design purpose. Always, because we can using the computer program to help us to get the best design we need. Otherwise, you use your hand calculation. Even you spend 1 day, 2 days, still it's not easy for you to get the best result. But through this optimization methodology, you can get better designs. The flow chart. So A is the manual design flow chart, and B is the computer-aided optimization flow chart. So usually, so you need to collect data. You need to get information by hand. Then you estimate initial design by hand. You analyze the system, and you check if your system is okay with all these criteria. Then is design good, satisfactory? Yes, then stop. If no, you need to update your design based on your experience or heuristics. Heuristics is similar to experience. The design history. Then go back to analyze. So you can do this by hand. Take weeks, maybe months to do this. Usually, take weeks or months. But for this optimization design process, okay, you get problem statement, you collect data, you by hand you get initial design, then you analyze this one, then you check your constraints, because we have design variables, but we have our limit, upper limit of the design variable or lower limits of the design variable. Those are the constraints. So you have your design variable, you have your constraints. Then you have your optimization process. Then if the design satisfies the criteria, yes, stop. Otherwise, update optimization process. So this one, we can use computer software, optimization software to help us to do this. Okay. Quite similar, but one is by human, the other one is by optimization software. Okay, so we need some terminology for you to do this design optimization. So if we have several points, like S1, S2 to Sn, we call this collection of these numbers n tuple. N tuple. If it's just S1, just one number. The design is one number. Just we design for length. A rope, we just care about its length. So we only need one variable, S1. So this is one tuple. But you want to design the desktop, you need length and width. You need to design variables for this desk, length and width. So we need two numbers, S1, S2. So we call it two tuple. So it's a name. Then for XYZ coordinate. If you want to describe a point in the space, we need 3 coordinates. We need S1, S2, X3. And this is column vector, and this is row vector. So S1, S2, 3 transpose. The row vector can become a column vector. Then, so this point, N is 3-dimensional. We can have a symbol. 3-dimensional space R3 means 3-dimensional space. R2 means 2-dimensional space. Okay, so far so good. Then sets. Sets, we have elements. A lot of elements can be in a set. So we have S1, S2, S3 for all the points in the space. But X3 must be 1. X3 must be 1. For all points, X3 must be 3. So all the collection of all these elements in a set. S is a set. X is components, elements in a set. So sorry, what's your name, please? Huh? 增远. Sheng Yuan. Could you read this? Yes. Continue. Good. So you will need to read this. So this is the way to read it in English. S equals the set of all points x1, x2, 3 with x3 equals 3. Kinder, could you read this?
Equals
The double quote.
S equals
Continue.
S equals the set of all points x1, x2, x3 with x3 is equal to 1, 3.
Okay. So for this example, we have a set S. So the S for all points satisfy x1 minus 4 squared plus x2 minus 4 squared less than 9. So x1, x2. So 4 is the center. For all points x1, x2. If all points satisfy this equation, means this is 9 is 3 squared. So this is the radius. For all points inside this circle, for all points satisfy x1 minus 4 squared plus x2 minus 4 squared less than or equal to 9, means all points inside the circle and on this perimeter belong to set S. And so in this book, the shadow area means outside our design space. So this is inside. So this is S, all points inside and on the circle belong to this set. Okay. So, Ami, do you understand? Ami, could you read this?
If a point X is an element of the set S, when we write X
Belongs to S. So S is an element of S. Belongs to. Okay, after me. Read after me. Read.
X belong to S.
Then, if S is a set, T is also a set, but S is inside T. S is a subset of T. We use this one. So we read T is a superset of X, or S is a subset of T. S is a subset of T, or T is a superset of S. Okay, R1, could you read this?
T is a superset of S.
Or we can write it another way.
S is a subset of T.
Okay, good. Then Einstein notation. So when Einstein formulated some complicated formulations, he used this notation, Si or Aizxz. So you don't need to write S1, A12, S2 plus S1 plus A1, 3, X3 plus X1. So you don't need to write another symbols. You can just use this one. S1, I from 1 to 2, and Z from 1 to 2. You can, so Aiz equals C. You can carry out S1, A1 to A11 S1 plus S1, A12 S2 plus S1, S2, A21 X1, X2, A22 X2. For I from 1 to 2 and Z from 1 to 2, see you have several items, but if N go to 8 and N go to 6, then it's too many. Out of your is too complicated. So we can use Einstein notation to simplify your formulations. Okay, so for this one, I from 1 to N, or you can read I goes from 1 to N. Again, would you read this?
I goes from 1 to N.
Okay, good. So Si is a scalar, but Sz, if you have this, means it's a vector. We have Z from 1 to K means we have K vectors. And they are X1, X2, T of S, K. So this one represents a vector. This one is a scalar. Sorry, but what's your name? Yes. Huh? Junhong. Junhong. Let me show you this one as an example. So C, so do you know how to fix the problem? Okay. Oh. Okay. So C equal to Xi, Aiz, Xz. So if I from 1 to 3, z from 1 to 3. And you can write x1. Remember, I the same, z the same. So I, z, and 2 the same means summation. A1 is A1, 1, x1 plus x1, A1. So remember, usually we start from 1, I the same, z. So I and z1, 1, then 2, x2 plus x1, A1, 3, x3. See, I1, z1, 1, 2, 2, 3, 3, plus. So this is the Einstein summation. Then next we take I equal to 2, x2, A2, then 1, x1, plus x2, A2. So z1, z2, x2, plus x2, A2, 3, x3. Then we have the third one. Because I from 1 to 3, z from 1 to 3, then plus x3, A3, 1, x1. Again, 1, 1, 2, 2, 3, 3. So total we have 9 elements. So this is Einstein's summation. Okay, the next one is the dot product, inner product, dot product. So the definition of dot product is x dot y. So we take x transpose times y. So x is a raw column vector. So say x is S1, x2, column vector. Inner product, y is y1, y2, column vector. So we do transpose. So column vector transpose becomes x1, x2, and times. So this is inner product. This is vector, y1. See, this is y1, y2. So main matrix calculation. First row times first column, S1, y1 plus x2, y2. But x1, y1 plus x2, y2, we can use this summation equal to xi, yi, sigma I from 1 to 2. Okay? You get it? Good. Junhong, do you get it?
Yeah.
Okay, Junhong. So could you read this?
Two vectors are sent to the orthogonal normal if the dot product is zero.
So if two vectors, the dot product is 0, means the two vectors are normal to each other, perpendicular to each other, or orthogonal to each other. Okay? Inner product 0 means they are perpendicular to each other, or normal to each other, or orthogonal to each other. You can use orthogonal, you can use normal, you can use perpendicular. The same. So Zheng Yi. So your name again? Zheng Yuan. Okay, second, could you read this one?
The vector are not orthogonal. The angle between them.
Yes, we can use this equation. S inner product 1, 2 vector. The definition could be x length, y length times cosine theta. So this one represents the length of a vector. Represent the length of a vector. We can call it's the norm of a vector, NORM. Either its length or norm represent this one. This one. Length of a vector or norm of a vector. So and so for this symbol, it has two names. Can you tell me what are the two names for this symbol? And what are the two names for this symbol? Do you understand my English? But do you know kind of what are the two names for this symbol?
Norm of the vector.
We have two names. One is norm,
Length.
length. Good. So maybe you need some time to get yourself comfortable in the classroom. Okay, what are the two names for this symbol? Okay. Then how to calculate the length of a vector? We can use this equation. If x is a two-element vector, x1, x2, then the length definition is square root s1 squared plus x2 squared. See I from 1 to n. If n is 2, then this is s1 squared plus x2 squared. And another symbol is x inner product x. Take square, so square root is this one, and this one is x inner product x. Because if x is s1, s2, this one is s1, s2. Inner product, we can take the row vector of this one, x1, x2 times s1, s2. So first row, first column, s1, s1, s1 squared, x2, x2, x2 squared. So it's s1 squared plus x2 squared. So it's the same as this one. Okay. So suppose now vector x I from 1 to 3. Then now could you go back to our room to take a stack of spare A4 paper? So, Hugh, do you know how to start the cell phone? Okay, for this case, you can write S1. For this one, see, X transpose is S1, X2, X3, row vector, and A is a 3 by 3 matrix, A11, A12, A13, A21, A22, A23, A31, A32, A33, and X is a column vector S1, X2, X3. So this is matrix. form. And this is the Einstein. Yeah, Einstein form looks like this one. Aij, xi, xj. If you see this one, yeah, this is Einstein notation. And this is the summation notation. And this one, see, x transpose ax, this is inner product notation. So x is x1, x2, x3, and a times x is, say, it's a 3 by 3 matrix. A1, 1, x1 plus a1, 2, x2 plus a1, 3, x3. Then the second element, a2, 1, x1 plus a2, 2, x2 plus a2, 3, x3. And the third element, a3, 1, x1 plus a3, 2, x2 plus a3, 3, x3. So we have different mathematical forms to say the same thing. Okay. Any problem? Junhao, do you understand what I'm saying here? So, do you understand what I'm saying here? Would you please help Junhao understand? And do you understand this? Could you explain to him? Okay, so Lan, could you turn it off? OK， 俊头右手边的同学，可以 Your name please。俊头左手边的同学，建福，燕如，Please read this one.
Throughout the text, it is assumed that all functions are continuous, and at least twice continuously differentiable.
Okay, thank you. So if function f(x) is a continuous function, continuous means, for example, for this case, see, in xy coordinate system, this is a function, this is x, fx. For x star here, this is x star. And this point is a x star. So if this function is a continuous function, means continuous at x star is at this point, from the left to the point, from the right to the same point. So means x star, fx at x star is continuous. So means any point. So for any point, so this is the distance between x and x star. If the distance is less than a small number delta, for any x point, is the x is very close to x star, means very close, very close, very close, means the function value difference is also a very small number. So the function value very close to f star, the functional value very close to fx star. Oh well.
setting 它连麦。
Okay. Could you read this?
What is continuous different authority of the function, and not only that it is different about two times, but also that it second the derivative is continuous.
Okay, for example, x cubic differentiate once is 3x squared. Then differentiate once more is 6x. And the 6x means it's twice differentiable. But twice continuous. Continuous means the second derivative is also continuous. See, x cubic second differentiation is 6x, but 6x is a continuous function. See, it is a straight line, it's continuous. You understand? Okay. So this function is continuous. This one is also continuous. But this one, see, means when x equal to x1, they are more than one value. Fx can be this one, can be this one, can be this one, can be this one. So fx is not a function, because a function means for each x we only have one fx. But for this case, at x equal to x1, we have several values of fx1, so it's not a function. Kaiser, do you understand? And for this function, see, it's not continuous. From the left, we can have value here. From the right, we have value here. So from the left and from the right, their values are different. So it's not continuous. It's not continuous. Okay, continuous function. Partial derivative means if fx is a function of x1, x2, x3, x4, but we only take differentiation with only equal, maybe we take differentiation with x1 or x2 or x3. So this is partial differentiation. Partial differentiation. And this is the gradient, definition of gradient. So gradient is a vector. See, this is a vector. So the definition for gradient is partial f partial x1, partial f partial x2, keep going till partial f partial xn. So it's a column vector. So this is the definition of gradient. Okay? The reason we need this because when we do the optimization, we need several properties, and we need the definition of this gradient. So you need to have you need to understand the definition of gradient. Also, for this symbol, ij from 1 to n means partial f, partial x1, partial x1. Then, so this one is a matrix. So we take this one here, matrix. If this is 3 by 3, means partial f, partial x1, partial x1, partial f, partial x1, partial x2, partial f x1, partial x3. Then the second row, partial f, partial x2, partial x1, partial f, partial x2, partial x2, partial f partial x2 partial x3. The third row, partial f partial x3 x1, partial f partial x3 partial x2, partial f partial x1 x3 partial x3. So this is a 3 by 3 matrix. Second differentiation. So we call this matrix Hessian matrix, HX. So this is the symbol for Hessian matrix. Walter, could you read this?
If f of s is continuous, different above 2 times, then a matrix h of s is symmetric.
Okay. Symmetric means, say for example, 1, 2, 3, 3, 2, 3, 3, 2, 1. So they are matrix. So this is diagonal, but H21 equal to H12, H13 equal to H31, H32 equal to H23. This is symmetric matrix. Do you understand symmetric matrix? Can you tell him symmetric matrix? Junho, do you know what is symmetric matrix? Symmetric. Okay. Okay, another definition, gradient matrix. So we have gradient for one function. For one function, we have a gradient. But so this G, we have G1, G2, G3 to Gn. We have multiple functions. So this one, we have G1, G2, G3. So the gradient matrix means this is a, say, this is a row vector. We have G1, G2, G3, G4, keep going. So the gradient matrix means, say, partial G1, partial X1, partial G1, partial X2, partial G1, partial X3, partial G2, partial X1, partial G2, partial X2, partial G3, partial X3, partial G3, partial X1, partial G3, partial X2, partial G3, partial X3. So this is the gradient matrix. Junho, you fall asleep. Okay, please write down a gradient matrix. G has 4 components, G1, G2, G3, G4. And we okay, camera up. Okay, we finished lecture 1. So looks like you are happy and enjoy this lecture. Then we will proceed to lecture 2. Lecture 2 is the optimization problem formulation. When you are given the problem, how you can formulate into the standard formulation. Then after that, we can use our techniques to solve the problem. So if you can formulate problem right, your solution is right. But if your formulation is wrong, then your solution will be wrong. So optimization depends on your formulation. How you select the design variables, how you create the constraints, the upper limit, lower limit of your design variables. That will determine your solution. So for optimization problem, there's no exact solution. There are many possibilities. Everyone can reach different solutions. Okay? So if you go to the iLearning, for lecture 1, you can find the textbook here. So the textbook is the 3rd edition by this author, Aurora, from Iowa City, University of Iowa. If you want to improve your English, by reading textbooks is the very good way to do it. And if you see if this sentence is very good, try to memorize and write down on your paper and memorize this sentence pattern. So reading is the best way to help you for your writing. By the way, English is fun. If you agree with me. Okay, this is a textbook. Then if you go to our iLearning for this optimization of design, course materials. So lecture 2, PPT. Okay, so it will be good if you can read the chapter 2 after we finish the chapter 2. You will get a better understanding of this chapter by reading it by yourself. Okay, Kaiser, could you read this first?
Process of transforming the design of a selected system and or subsystem into an optimum design problem.
Yeah, we transform the problem to a optimization formulation. So it's they are very. We have procedure to do that. And we have 2 case studies: design of a can and a sphere tank design. So what's your name? Xiang Yu. Could you read the first one?
Purpose, differential and formulation of the problem take regular 15% of the total effort need to solve it.
Okay. So formulation maybe is very important. But like what I said, formulation right, solution right. Formulation wrong, solution wrong. So say 50% of the work is problem formulation. So, sorry, what's your name? Guan Cheng. Did you read the second one?
It is the goal to follow your 5 procedures for formulating design optimization problems.
Yes. So we have some formal procedure for you to follow. So it's better you follow this procedure. You don't need to be too creative. So, okay. Hugh, could you read this?
Optimal solution will be only as good as the formulation.
Yes. How good your formulation is, then how good your solution will be. Lai, could you read this?
It will probably to include the risk program strengths in the formulation, the optimal solution is applied to private in.
Yes. So constraint means the limit of your design space. So, or the limit of some design constraints, some upper limit, lower limit. If you miss one important constraint, you may lose the whole point. Again, could you read this final one?
If we have too many constraints or if they are inconsistent, they may be non-simple.
Yes, so too many constraints will be a problem. So keep it simple is important. Okay, now it's the process to do it. So the first one is the problem statement. Probably this is given by your boss. Your boss can give you this and ask you to do the formulation. And could you read the first point?
Translate encrypt the statement of it into a well-defined statement.
Yes, usually for engineer, we need some mathematical statement. But for ordinary people, they just use ordinary sentences to describe the problem. So as an engineer, you know how to convert the ordinary language into mathematical formulation. Kaiser, could you read the second?
Optimization methods are iterative where the solution process is started by selecting a trial design or a set of trial designs. The trial designs are analyzed and evaluated and a new trial design is generated. This iterative process is continued until an optimum solution is reached.
So Kaiser, so I would suggest you, optimization methods are iterative. Take a breath. Where the solution process is started, take a breath. By selecting a trial design or a set of trial designs. Okay, do this again for the first sentence.
Optimization methods are iterative where the solution process
Stop. Remember what I tell you? Optimization methods are iterative. Look at me. Where the solution process is started, by selecting a trial design or a set of trial designs. Okay, do this.
Optimization methods are iterative where the solution process is started by selecting a trial design or a set of trial designs.
Okay, yes, slow down. Take a break. Take several breaks. What happened? But, you know, I kind of appreciate you five come to help. So, still I feel thankful to you. Okay. So, for optimization problem, we need trial solution. Means we need to have some initial point, and this initial point, they can create some good solutions. Not very good, but you know it's a good starting point. So trial solution is you need to try to get some trial solution by hand first. After that, we go through this computer programming iterative process to improve our initial solution to the optimum solution. So what this is all about trial design, trial solutions. So you need to have some initial design anyway. Otherwise, the process cannot start by itself. So we need a startup circuitry anyway, like this, the initial solution to run. Okay, 5 steps. So you should follow these 5 steps. Design, implementation, formulation, step. Okay, step 1. Like, could you read step 1?
Step 1. Project problem description.
Step 2. Data and information collection.
Step 3. Output design variable.
Case for organization,
Criteria. 俊宏
Formulation of calculation.
俊宏 you know why I remember you? Because your name is very popular,
Yeah.
easy to remember. Okay, 1, 2, 3, 4, 5. So step 1 is description, just ordinary language, just a description of the problem. But step 2, we need to collect the data. We need to find out the material properties. We need to find out the material property or the formulation, blah, blah, information. We need to get information. And step 3, define design variables. What are the design variables? We can change. And step 4 is select the criteria. Use genetic algorithm, or use simulated annealing, or use linear programming, or use nonlinear programming. We don't need to do the programming by ourselves because they are everywhere. The package, implementation package. So this one, we just get the software to do it. Then after that, constraints. You have design variables, but not the design variable cannot be any value. We need some upper limit and lower limit. Those are the constraints. The constraints of all these design variables. Okay? Okay, step 1. Problem description or project description, either way. Ami, do you read this?
The statement describes the overall objective of the project and the requirement to be met. This is also called the statement of work.
Okay. See, the statement you need to, this is the keyword objective. So the objective could be your objective function, your goal, design objectives. And the requirements, if you see the requirements means there are some constraints of your problem. So design constraints might come from here, and design goal comes from here. So this is step 1, problem description. Okay, so we have a problem. So this is the problem description. Awan, could you read this?
Consider the design of hollow square cross section can be ever been to support a load of 20 kilonewton at its end. The beam made of steel is 2 meters long.
Okay, good. So I want to design this beam. And this beam has a cross section, a hollow cross section. And the goal, see, or the constraint is the load of 20 kilonewton at the end. And the material is steel. And the length L is 2 meters long. So we want to design this one. See, now you can tell probably design variables because L is fixed. So what we can plan this width. This is the width, and this is the thickness. So probably W and T are the design variables. So the problem description. Then after that, we need to collect information. So this is the information we need to collect. The fail criteria, the fail condition. So the material should not fail under the load. It cannot fail. So this is one consideration. And also we want to consider the deflection should not be more than 1 centimeter. Also we have some constraints. The width W in this range, the thickness in this range. So these are the constraints. Also minimum mass beam. When you see the minimum or maximum, that's the design goal objective. So the minimum mass, we want minimum mass. So we need to design W and T to have the minimum mass. So minimum mass is the design objective. And design, we need to select the upper limit, lower limit for the design variables. So these are the information we need to collect. We need to know. You can ask your advisor, okay, do you have this requirement? So your advisor may give you the requirement. So these are the design constraints. So data collection, information collection. Okay, could you read this?
Requirement result in the course of when many days and so forth.
Yeah, we need to see the steel, what are the material properties, the density, the Young's modulus, the yield strength, material properties, and the cost for this steel. What's the cost? Because we always want to reduce the cost. So we need to analyze the trial solutions. So analysis procedure and analysis tools. So we need to know those mechanics materials. If you know the load, how can you calculate the deflection? Because the deflection cannot be too large. So we need some tools, some analysis procedure, analysis tools to help us to solve the problem. So this is data collection. So now, more information. Kaiser, could you read this?
The information needed for the cantilever beam design problem of example 2.1 includes expressions for bending and shear stresses and the expression for the deflection of strain.
Yes. See, we need equation about this is the deflection. Load P, length L, Young's modulus E. This is second moment of inertia. Use this equation, we can calculate the deflection. Junhong, what it is? Deflection. And this is shear stress. And this is the moment, M equal PL. And this is the shear stress. This is the stress, normal stress. This is shear force. This is moment. This is normal stress. And the I is the second moment of inertia. And Q is the first moment of inertia, because we need to Q to calculate shear stress. We need I to calculate the deflection. And this is the cross-sectional area. So all these mathematical formulations are the equations we need to help us to solve the problem. Okay, all these parameters. Then step 3, design variables. Could you read this? The first one.
The first one, identify a set of the variable that describe the system for the design variable.
Yeah, in this problem, Euler's W and sigma T are the design variables. They are the variables we can change. Because we change W and T, we can change the cross section. Because we want to minimize the mass, but the length is fixed. So the only thing we can do is to change the width and the thickness. So naturally, we will select width and thickness as the design variables. Hugh, could you read the second point?
The number of dependent design variables creates the design degrees of freedom of the problem.
Yeah. So we have 2 design variables, means we have 2 degrees of freedom to change. Like, could you read the third one?
Example 2.3 design variables for the cantilever beam. W equal width, depth of the section, millimeter. T equal wall thickness, millimeter.
Yeah, we have 2 design variables. So step 3, design variables. Then step 4, optimization criteria. So this one is the design objective. What is the objective function? We want to minimize the mass. So, but the length is fixed. So we want to, which means we want to minimize the cross-sectional area. If the cross-sectional area is minimized, means the whole volume is minimized. If the whole volume is minimized, means the whole mass is minimized. So it all comes down, we can see minimize the objective function. Okay, so step 4, objective function. Step 3, design variable. Step 4, objective function. And step 5 is the design constraints. Optimization. Okay, for the objective function. So what's your name? Guansheng. Guancheng. Could you read this?
For the design problem in example 2.1, the objective is to design a minimum mass can beam since the mass is proportional to the cross sectional area of the beam. The objective function for the problem is taking us the cross-sectional area.
Yes, the cross-sectional area A is the objective function. We have 2 design variables, WT design variables. F is the objective function. We want to minimize this objective function. So this is cross-sectional area. The cross-sectional area is W minus T. So we have 1, 2, 3, 4. We have hollow. So W minus T times T times W minus T. So you can do this. Because W minus T times 4, 1, 2, 3, 4, and the thickness T. So this is the cross-sectional area. But anyway, you can do this by yourself. Then the constraints. So your name,
深远
Sung-Yuan. The first one.
All restriction based on the design are comparatively cost constrained.
Yeah, constraints are the restrictions of the design. Huh? Okay, this one.
Many constraint functions have only first order term in design variable. Those are called linear constraint.
Okay, Junhao, this one.
Programming problem has only linear constants and objective functions.
All general problems have nonlinear cost and all constraint functions. These are called nonlinear programming problems.
Okay, so linear means ax plus by. That's all, no square term or no cubic term, no higher order terms means linear. If all constraints objective function is linear, so if objective function and constraint they are linear, there's no higher order terms, so linear programming. So other than that, with nonlinear programming. Okay, Hugh, could you read this one?
Design means all requirements equal to a feasible result.
Feasible design means the design solution meet the constraints, all constraints. So they are feasible, usable, useful design. So feasible, keyword, feasible. Okay, so if we have two design variables, x1 and x2, if the design x1 and 2 must be on this line, so this line is x1 equal x2. So design must be on this line means this is equality constraint, means they need to follow this x1 equals x2 exactly. So this is equality constraint. For this one, x1 and x2, two design variables. But for x1 and x2 in this region, they are all feasible, possible. So this is feasible region for x1 less than or equal to x2 here, and here are not feasible. So this is inequality constraint, means inequality constraint. This is equality constraint, okay? Some terminologies you need to know. Okay, so the constraints, the stress must be less than the yield stress. If the stress is larger than this value, design failed. Okay, so this is the bending stress constraint. A shear stress constraint means this is maximum shear stress, tau A. So this is the shear stress. Second constraint, if the stress is larger than this one or this one, you will be in a break. And this is the deflection. The maximum deflection must be less than this value. If the deflection is too large, maybe for our function, it might be an actuator. But if the displacement is too large, then we don't like it anyway. So this is the maximum deflection. And okay, but otherwise, we have W divided by T should be less than or equal to 8. Okay, we set this design constraint. Also, the lower value, 60, the upper value, 300 for W. and the lower value 3 for thickness, and the upper value 15 for the thickness. So we can turn this one into this form, W minus AT less than or equal to 0. So remember, all constraints less than equal 0, 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 less than equal 0. This is the standard formulation. Okay, now could you read this?
Plus the optimization problem is to find W and T to minimize the cost function subject to the A equality constraints.
Yes, see, you can count. We have 1, 2, 3, 4, 5, 6, 7, 8. We have 8 in equality constraints. There's no equality constraints. We have 8 in equality constraints for this case. Okay, we will have a break. Let's come back to the classroom around 3:30. Okay? Design of a can. So you have a can. We have a diameter and height of a can. You can expect Coca-Cola or Pepsi. We have aluminum can. So inside we can put liquid. So we want to minimize something. So you can imagine for the can, we want to minimize the surface area. We can save the material, the aluminum material. So design of a can. So first, your advisor can tell you what are the problems. Hugh, could you read the first?
The purpose of this project is to design a can to hold at least 400 milliliters of liquid.
Yes. See, if you see at least, you know this is a design constraint, at least 400 ml. Could you read the second?
The cans will be produced in the billions, so it is desirable to minimize their manufacturing costs. Since costs can be directly related to the surface area of the sheet metal used, it is reasonable to minimize the amount of sheet metal required.
See, you see minimize, another key word. This might be the objective function. The objective function is to minimize the amount of sheet metal. Okay, probably you know what's going on. Sorry, your name? Guan Shen. Guan Chen. Okay, please, this one.
Fabrication ending
Aesthetics.
aesthetics and shipping consideration import the following nutrition on the side of the can.
Okay, stop, please. Verification. We make, manufacture, handle it. See, your hand to hold, so you must feel comfortable. Handle it. Aesthetics. Looks beautiful. Aesthetics. Aesthetics. Shipping consideration. We need to put them in a box or a ship container and ship to other countries. So it's also a constraint. So now, due to this, let's decide what's going on. Your name, please. Seng Yuan. This one.
The diameter should be not more than 8 centimeters and no less than 3.5 centimeters, whereas the size should be no more than 18 centimeters and no less than 8 centimeters.
Okay, in order to hold, the diameter cannot be too large. So the diameter should be less than 8 centimeters. We cannot be too small, otherwise it may drop. So 3.5 centimeters. So you know, these are the constraints. design variable constraints. They appear here. So objective function, constraints, and this is another constraint. So you have some idea about this problem. So now the second step is to gather information. Okay, data and information. You need to collect them. Sorry, your name?
相遇
Xiangyu, please.
material fabrication handling estimate and shipping consideration.
Okay, those are material property, aluminum, maybe, and fabrication, those consideration. So yeah, okay. Then design variables. Two design variables, because remember diameter constraint, and height constraint, and volume constraint. So we need CDN. Diameter and height are quite reasonable to select as our design variables. Step 4, objective function. See, we want to minimize the surface area so this is the surface area, the top and bottom area times 2. And this is the circumferential area, pi d h. So this is the objective function. Step 5, constraints. Okay, constraints. Volume should be not greater than 400. Okay, so constraint. Then diameter constraint, height constraint. Okay, so we got the formulation. Junhong, you are the only guy I can remember. 相遇，生源，冠城，谚语，燕如。I will forget after 10 minutes maybe. At least now I will remember. Junhong, please read this.
There are 4 constraints Thus, the problem has 2 design variables and a total of 5 creative constraints.
So pi is 5. 1, 2, 3. But because this one, d greater than or equal to 3.5, consider 1. And d less than 8, another one. So 1, 2, 3, 4, 5. So we have 5 inequality constraints. Okay, now we are all set. Then another case. We design a tank to put the gas, deposit gas inside. The tank's design. 谚语，谚如. Could you read this?
The goal of this project is to choose an insulation thickness to minimize the life cycle cooling cost for a spherical tank.
Okay, a spherical tank looks like a ball, circular ball, spherical. So, see the goal, minimize the cost, cooling cost. Okay, we know minimize. So this should be the objective function. And to choose installation secret T. So T should be a design variable. Ami, this one.
The cooling cost include installing and running the refrigeration equipment and installing the solution.
Okay, so we have spherical tank. We want to put the installation material on the surface so the heat won't get out because we need to put the gas in some temperature. So we need a heater, but we don't want to heat always. Otherwise, it will cost a lot of money. So we want to have the installation there. So the cooling cost is okay. We need to install the installation. That's money. Then we need to running the refrigeration equipment. We need to run the cooling or heating. So electricity, power. Water, this one.
Assume 10 years left, 10% loan interest rate, and no select is
Okay, we want this tank to use for 10 years. Then, but we borrow money from the bank to build the tank. Then we need to pay the interest. So the annual interest to the bank is 10%. And after 10 years, salvage value means you cannot use it. There's no value anymore. After 10 years, the value is 0. No salvage value. One, this one.
Tank has already been designed, having and as this really
Okay, the radius of the sphere, the tank, is fixed. So we can only play with the thickness of the insulation. Okay, so these are the problem statement from your boss. Then the data. So we need some data, we need some information. So we need to have this equation to calculate the total surface area of a sphere, 4 pi r squared. And the cost, the capacity of the refrigerant equipment. Because 1 year, 365 days. Each day we have 24 hours. And delta T is the temperature increase of the environment. Say, our environment, the temperature may increase, decrease, but we want to keep the temperature inside constant. So this will be the cost. Delta T large, higher cost. A is the total surface area. If it's very large, cost more. And T is the insulation. If you have the insulation thicker, then you could lower the heating cost. So T is T1 is the conductivity, is the material property. So this is the heat consideration. So this is the information we need to collect. So you can read this by yourself. Okay, now step 3, design variable. The only one, the thickness of the insulation. Step 4 is the objective function. We want to minimize the cost. So the cost is a function of AT. A is the surface area. T is the thickness. So this one is the insulation material cost. And G is the heating energy cost. G is also, so you don't need to worry too much about this. Just, this is the heating cost. This is the material cost. And this is about interest rate, so you don't need to worry about it. So see 10 years and interest. So you can use this one to calculate the money you need to pay to the bank. Okay, we will leave it there. And constraints, step 5. Okay, did you read the first one? So T should be greater than 0, right? Thickness. And to read this,
have a strict in the queen. They cannot be strict. Not because they are number the play a solution.
Okay. So we set t greater than 0, but for numerical simulation, t greater than 0 is we will have convergence problem. When you do the numerical integration or differentiation, so we try to set a t minimum, a very small number, but not 0. If this is 0, numerically, it will have problem when you use a software to solve the Newton-Raphson or Newton whatever. Yeah, it will have problem. So it's better to not use a very, you should use some very small number other than 0. So I ask Kaiser every day, every morning before 9 a.m. to send me a link of Voice of America that he studied every day. So after almost several months, he improved a lot English. So I require you to do the same thing. Every morning before 9 a.m., you can tell him the VOA and study the VOA every day, just one session. So I can see the difference for Kaiser, because 4 months ago, it's not easy for me to communicate with him. But now we are okay, all right? They will help you. So to start from tomorrow. Okay, so this is the constraint, step 5. Okay, we'll skip this. Final formulation. This is very, if you can give your advisor, your boss, this page to summarize everything, just use the mathematical description. They'll be perfect for any optimization problem. See the data, the parameter you will use, and design variable, Tn, objective function, minimize this one, and the constraint, t greater or equal to t minimum. Very simple, but it tells everything. So this is the engineer job, to use mathematics to describe your problem very precisely. So remember, delta, design variable, objective function, constraints. That's all. Okay. So they will see, this is the format for optimization problem. This is the standard for, if you read a journal paper, if it is related to optimization, almost everyone follow this language. We use this standard language in a journal paper. So this is what you need to, if you write any paper related to optimization, you will see this in almost all papers. Minimize objective function, subject to the equality constraints, and inequality constraints. See, so equality constraints, hi equals 0, I from 1 to p, and n in equality constraints less than equal 0. Always use less than. Formulate your problem less than or equal. And objective function, fx equal, and x is a design variable. So design variable here, objective function, equality constraint, inequality constraints. So this is the standard formulation. Kaiser, could you read this?
The number of independent quality constants must be less than or at the most equal to the number of design variables.
Yeah, see, equality constraint, if you have 3 design variables, but if you have 3 equality constraints, 3 equations, 3 variables, then only one solution, right? You don't need to do optimization at all. So P must be less than or equal to N. Otherwise, you don't need to do optimization. So Hugh, could you read this?
When P smaller n, the ultimate solution for the problem is possible.
Yes. So you have 2, 3, or 4 solutions. You can select from those different solutions. Right, do you read this?
When D equal N, no optimization of the system is necessary because the root of the equality constraints are the only candidate void for optimum design.
Yes. 冠成 Yes, 冠成 Okay, this one.
When
Greater than.
greater than we have n over the determinant system of equation, no solution for the design problem is possible, and the problem formulation need to be closely
Examined.
examined.
If you have 3 equations, but you have only 2 variables, then over-constrained, over-determined, like, so no solution is possible. So you need to go back to formulate your problem. Okay? Good. Excellent. Shen Yuan. The first one. Okay, for this point, let's go back to our here. See, we have an inequality constraint. So all design variables here are feasible. And design here violate these constraints. So if you do your optimization, eventually you got your ultimate point. If your ultimate point is here, so this is inequality constraint, but your ultimate point is on this boundary. So this inequality constraint is active. If your ultimate solution is here, your start solution. Your start solution is not on this inequality constraint. It's not on this boundary. Means this inequality constraint is inactive. Okay? So this is the point. Okay. Xiangyu, do you read this? Okay. Oh, sorry, we read this already. So in this point, X star is unsatisfied this one. Equal means this inequality constraint is active. Junhao, you're the final one. We start from you, we end with you. This one, could you read this one?
equality constraint Q over small equal zero is said to be inactivity at the design point is start. If it is scripted satisfied.
Okay. See, English, if you read this without that figure, it's not easy to imagine. But with the help of the figure, it's easier for you to have a picture of it. So Okay, this is the, it is not on the boundary, means this base inequality constraint is inactive. Okay, so this concludes our lecture 2, and also conclude today's lecture. So it would be great if you could read chapter 1 and chapter 2 of the textbook to improve your English. Okay, that would be great. So give me the A4 paper with your name and student ID on it, and I'll see you next Thursday. Thank you. Okay, please.